Section 10-4, changes of state. Here's a quick lecture on this, and you guys can use this to help you study. And the reason why I'm doing this is because some of the stuff in this chapter is a little bit more than information, so I want to throw it out there and at least explain it to you. Okay, let's get started. Changes of state and equilibrium. A couple questions I'm asking you here. What conditions are necessary for evaporation to occur? So we have to understand evaporation is that it's the natural loss of water off the surface of a liquid into the gas phase. Well, believe it or not, if I have a beaker, it's got some water in it, blue for water, evaporation is only going to occur at the surface. Okay? What happens is the natural energy that this is absorbing, or the energy that's inside here, is going to cause some of these particles to gain just enough energy to escape. Now, how much energy is that? Well, it's energy equivalent to about 100 degrees Celsius. Not every particle is the same temperature. The average temperature of this room temperature water would be about 22 degrees Celsius, but some particles are on the hot side, screaming hot, maybe at 1,000 degrees Celsius, who knows, and some of them are super cold, maybe at negative 30. The idea is that those particles at the extreme temperatures are not plentiful. There's just a few of them, so it doesn't really weigh in, but the average temperature is where most of the particles' temperature are about 22 degrees Celsius. So you have to have enough energy to escape. The second thing is attractive forces for the water. One water molecule is going to attract another through something called hydrogen bonding, which I believe we studied in chapter 5 or 6. With hydrogen bonding, water attracts another water molecule, so those attractive forces have to be overcome. Then, once those two things happen, then the evaporation can occur. Okay, let's look at another physical change, a change of state. Here we have what conditions are necessary for condensation to occur. Well, condensation, if you remember, is where you have gaseous water that collects on the outside of like a cold Pepsi can in the summertime. So that water on the outside, that's condensation. And what has to happen is those particles have to slow down enough. Their temperature has to slow down enough. Temperature can be is a measurement of kinetic energy, or how fast the particles are moving. So if the temperature drops of those particles, or the kinetic energy drops, then the particles will collect on the side of the container. Okay? Next, changes of state and equilibrium. The first thing we have here is, let's talk about a phase. A phase is a part of a system with uniform composition and properties. So a phase could be solid, it could be liquids, or it could be gases. Okay? Equilibrium. Now, here's the thing, and I've italicized a few words. It's a dynamic condition. Dynamic means it's constantly changing, in which now two opposing conditions, that's the next thing I have to point out here, two opposing conditions. Now, since we're talking about changes of state, it could be evaporation versus condensation, or freezing versus melting. Those are the two opposing conditions, and they're going to occur at equal rates. So they will be, if you have an equilibrium of students in my room, let's say you have 10 students on the inside of the room and 10 students on the outside. So the two opposing conditions, dynamic means they're going in and out. The two opposing conditions is in versus out, and at equal rates means that if a student goes out, another one has to come in. Or if two of them go in, then two have to go out. And it has to be a closed system. In other words, it's just my room and just the outside of this hallway here, okay? Equilibrium vapor pressure. Now, this says the pressure exerted by a vapor in equilibrium with its corresponding liquid at a given temperature. Okay, well, what does that mean? Again, in equilibrium vapor pressures, let's say we go back to our beaker, okay? Since at equilibrium, we have to have a closed system, so let's put a cap on it. And what this is that at a certain temperature, let's say in this room right now, it's about 22 degrees Celsius, evaporation is going to happen at an equal rate as condensation. Okay, so that's the equilibrium. Now, after a while, at 22 degrees Celsius, and I got to keep 22 degrees Celsius, don't change the temperature because it says at a given temperature. Then I will have a vapor that will collect up here, and that will exert a pressure. That is my equilibrium vapor pressure. Now, if I change this temperature and I go up, then I'm going to have more evaporation and the equilibrium vapor pressure is going to be higher. If I drop the temperature, the equilibrium vapor pressure will be lower, okay? So what does this question say? What happens when temperature is increased? Obviously, the equilibrium, there will be more evaporation. Therefore, there will be a higher equilibrium vapor pressure. If kinetic energy increases, the vapor pressure increases, and equilibrium vapor pressure is established at the higher temperature. So this is the answer to this question here. Okay? Next. Equilibrium vapor pressure / evaporation in a closed system. All right? All right. If we take a look here, you'll notice that this is an open system right here. Okay? There's no cap here. I see the cap. Now, you'll notice that if with no cap, I have more evaporation, 4 arrows pointing up, and only a little bit of condensation, 2 arrows pointing down. So this is not at equilibrium. It says no equilibrium. Okay? Once I cap it and I let time go by a little bit and I keep the temperature constant, wow, my computer's really running slow here, constant, temperature has to remain constant, then I will have as much evaporation as I will condensation. Okay? So I don't know what this Yaz business is here, but there will be an equilibrium. Okay? So it has to be capped, and there has to be time that follows. All right, next, changes of state and equilibrium. Again, equilibrium is just two opposing forces. It's dynamic. That's happening at the same rate and the same temperature if we're talking about equilibrium vapor pressure. So here it says vapor pressure and equilibrium vapor pressure are specific to a liquid, which is absolutely true. Okay? Why? Because every liquid's a little bit different. Water's different than gasoline, and gasoline's different than ethanol, and ethanol is different than molasses. You name it. They all have different things. So what are these differences? The attractive forces inside these liquids are always different. Molasses must have stronger attractive forces than water does because it's stickier. So if I have something that has very strong attractions like molasses or syrup or something like that, if they're attracted very strong, it's not going to evaporate much. And if it's not going to evaporate much, it's not going to produce much of a vapor pressure above that surface of that liquid in a closed system. If there's weak attractions like alcohol, alcohol evaporates very quickly, so it must have weak attractions with those particles. Therefore, they will have a high evaporation rate, and it does evaporate very quickly. And if it evaporates very quickly, then it will have a high vapor pressure and establish a high equilibrium vapor pressure in a closed system. The last thing about some of these changes of state is a volatile liquid. And a volatile liquid is not something that blows up, although it is somewhat synonymous. Holy moly, what's that? That's going to cause my computer to move very slowly. Anyway, volatile liquids is something that is not explosive. It is something that evaporates very quickly. So liquids that readily evaporate due to weak attractive forces. So weak attractive forces right here are going to be volatile. Okay, next. Boiling. The boiling is a change of state. But boiling is a little bit different than what you might expect. Boiling is a change of state within the liquid and at the surface. Okay? So where evaporation, let's draw a little picture, can only happen at the surface right here, boiling can happen inside, it can happen on the surfaces, and, on the edges here, and it can happen at the surface. So boiling can be a change of state at the surface or within the liquid. Then a boiling point is the point in which, now this is weird because you would say it's the point at which there is a transfer or a change in the state, but that's not true. Boiling point is the point, the temperature, in which the equilibrium vapor pressure equals the atmospheric pressure. So equilibrium vapor pressure must equal the atmospheric pressure. Now, let me talk about this for a little bit. I can get something to boil at room temperature if I want. Okay? We are used to water boiling at 100 degrees Celsius. Why? Because we are typically living in 1 atmosphere of pressure. And we're going to get to that in chapter 11. So at 1 atmosphere of pressure, water boils at 100 degrees Celsius. Okay? But what if if I could drop the pressure to like 0.5 atmospheres? Conceivably, water would boil at half that, about 50 degrees Celsius. 50 degrees Celsius is lukewarm. And then if I can get down to absolutely no pressure at all, 0 atmospheres, I can get gas to boil at 0 degrees Celsius, or roughly room temperature, 22 degrees Celsius. Okay, I can actually prove this to you. I can actually show this to you where water will boil, and it's not hot. So you have to have the amount of equilibrium vapor pressure coming off the surface, pushing up, equalizing the atmospheric pressure from the atmosphere pushing down. Once those two are equal, water will boil. So how do I get water to boil what we're used to? I have to increase the temperature of water. And I do that by applying heat. And when I apply the heat, the equilibrium vapor pressure goes way up. And when it does that, water boils. So we're used to boiling as something being hot, but it doesn't have to be. If you have any questions on that, make sure you ask me and I can address the classes on that. All right, now at boiling point, let's talk about this right here. At boiling point, all energy absorbed is used to evaporate the liquid. The pressure on that liquid must remain constant. So obviously we have an open system here. So any energy that goes in is dedicated to changing the phase. Let me say it again. Any energy that goes in, absorbed, is used to change the phase from liquid